Hi everyone and welcome to the video on anti-differentiation. Now this process is the opposite of differentiation, so we're going to have a look at it and see how we can figure out the patterns that go on in these kinds of problems. For the purpose of this video, I'm only going to be considering polynomials and we'll get into a few different things there, but that's going to be the main focus of this video. So to actually figure out anti-differentiation, what I'm going to do is I'm going to start off by thinking about what happens in the process of differentiation. So I've set up just a bit of a problem here, so consider these different derivatives. So the derivative of x squared is the first one, and when we do the derivative of x squared we get 2x. And the next one is the derivative of x squared plus 5, but again that's just going to be 2x, because the 2 goes in the front of the x, but then the 5, it's a constant, so it just disappears. The third one, d dx of x squared minus 3, so again that's just 2x, because the 3 is just a constant again. And d dx of x squared plus the square root of 7, again the square root of 7 is just a constant, so we're going to be left with 2x. So we can see that when we differentiate that x squared we get 2x. But all of those problems, they all had an answer of 2x. And so if I go the other way, and if I have a look at the antiderivative, so this symbol is used for the antiderivative of 2x with respect to x. Now it's really important when you're writing these that you include the dx sign on the end, because that's telling us that we are anti-differentiating with respect to x. But when I do that, I know that the 2x is always going to give me an x squared. The problem is, it might have been an x squared plus 5 that I started off with, or it might have been an x squared minus 3 that I started with, or it might have been an x squared plus root 7. I just can't know. And so I also have to actually include in my answer a plus c. So c is just a constant, and that constant could also be 0 like it is in this first problem here. But we have to write it there just because we have to be considering the possibility that there was a value there initially when we differentiated, and so when we anti-differentiate we put that back in there. Now I've put the title of this as anti-differentiation with integration in brackets, so anti-differentiation and integration are both names for the same process, and so if you hear me say integration or integrate rather than anti-differentiate, then know that that is just what I'm talking about and it means the same thing. Okay, so what I'm going to do is going to have a look at a couple of problems now. So the first one, if dy dx is equal to x squared plus 7x minus 5, find y. So to go from dy dx back to y, I need to anti-differentiate. So I'm going to write y equals the antiderivative of x squared plus 7x minus 5, and remembering to write the dx on the end of it. And when I anti-differentiate this, now what's x squared going to become? Let's just duck back up the page for a moment, because we need to consider the general sort of rule here. Okay, what's going to happen if I have x to the power of n dx? So what happened in this problem just here? The 2x became an x squared, so we raised the power by 1, but we also had to cancel out that 2 that was out the front. And so what's actually happening is we are raising the power by 1, but we're also dividing by that raised power. This is the opposite of differentiation. So rather than decreasing the power, we increase the power. Rather than multiplying by the power, we divide by the power. And again, it's always important to write a plus c on the end. So if I come back down to this problem now, I can apply this rule right here and figure out what the answer is going to be. Notice that the power and the number that's being divided by will always match up. So x squared is going to become x cubed over 3. 7x is going to become 7x squared over 2. And minus 5, well, that's actually a constant, and so when we anti-differentiate, it becomes 5x. And again, I need to make sure to write plus c on the end. The next problem, if f dash x equals x to the 4 plus 5 on x cubed, find f of x. So, to go from f dash x to f of x, I need to anti-differentiate. Alright, f of x equals the antiderivative of x to the 4 plus 5 over x cubed dx. Now the problem is that I can't work on that as it is at the moment, so I need to sort of simplify it first. And we do the same process here as we did with differentiation. So that is that we divide each of the terms to begin with. So when I do this, I'm not actually anti-differentiating it, I'm just simplifying, so I'll leave that integral sign there. X to the 4 divided by x cubed is just x. 5 divided by x cubed doesn't go nicely, so I just leave it as 5 on x cubed. And again, remember to write the dx there. But I still can't work with this because I've got a 5 over x cubed. I need to change the form of that using the index laws. So that is the antiderivative of x plus 5x to the minus 3 dx. Now this is in a form where I can work on it. And so I'm just going to integrate this now. So I don't need to write the symbol anymore. X becomes x squared on 2. And 5x to the minus 3 becomes 5x to the minus 2 over minus 2. And again, remember to write the plus c. Now there's a little bit of simplifying that can go on here. So all that I need to do now, I'll leave the x squared on 2 as it is. You might choose to write it as half x squared, that's also acceptable. I've got a plus 5x to the minus 2 on minus 2, so it's a positive divided by a negative, which will make it a negative. And I'm also going to move the x to the minus 2 into the denominator. So it's 5 over x to the 2. So by moving it back down the bottom, it changes the power back to a positive number. And again, I've got that plus c on the end. That was quite nice, left the perfect amount of space for it. So the last one, evaluate the antiderivative of 2 root x. So this one here, well, again, we can't work on this as it is at the moment. I need to write this with its index. So that's equal to the antiderivative of 2x to the power of half dx. So I've just changed the form of it, and now I can anti-differentiate. So that's equal to 2x to the power of 3 on 2. And that needs to be divided by 3 on 2, which isn't all that nice. And then again, we have a plus c at the end. So 2 divided by 3 on 2, how many 1.5s are there in 2? I'll do this just off on the side. So 2 divided by 3 on 2 is the same as using stage change flip, 2 times 2 over 3, which is 4 over 3. We only multiply that whole number into the numerator. And so what we end up with here is 4/3 x to the power of 3 on 2 plus c. X to the power of 3 on 2, now the fact that it's over 2 tells me that it's a square. I'm going to write this back in its surd form. Just so you're aware, this work that I'm about to do now would be considered additional engagement and is really discouraged on exams unless the question is saying to show that the answer is this kind of form. So I'm going to do it anyway just because it's good for your algebra skills to see it. So that is 4/3 times the square root of x cubed and then plus c. And that would be the final answer. So again, the fact that it's the power was over 2 tells me that it's a square root, and the 3 just stays inside it as a cube. Anyway, I think that's about all for the anti-differentiation work. So I'm going to leave that there and see you in the next video.